The drill bit enters the seabed and does not stop. It keeps going, through rock, through pressure, through one of the most geologically hostile corridors on the planet, until it reaches the other side of a strait that has divided two of China's most important regions for all of recorded history. What comes next will change how 100 million people move. The Bo Hai Strait crossing is China's most complex infrastructure undertaking in a generation. A rail tunnel running under open ocean for a distance that no country has ever attempted before. And the engineers building it are solving problems that did not have solutions when the project was first proposed. For decades, the Bo Hai Strait sat between two worlds. On one side, the Shandong Peninsula, one of China's most densely populated and economically productive regions. On the other, the Liaoning coast, home to Dalian, a major port and industrial hub. To travel between them by land meant looping around the entire Bo Hai Sea, roughly 1,500 kilometers by rail, nearly 12 hours by train. By water, the crossing is just about 106 kilometers. That gap, the difference between what geography offers and what infrastructure allows, is what the Bo Hai Strait Tunnel is designed to close. The project, reported to cost somewhere in the range of 200 billion yuan, equivalent to roughly $26 to $30 billion at recent exchange rates, would connect Dalian in Liaoning province to Yantai in Shandong. When complete, a journey that now takes the better part of a day would take approximately 40 minutes. 40 minutes across open ocean. Under the seafloor, China's National Development and Reform Commission has discussed the Bo Hai Strait crossing in infrastructure planning documents for years. The project appeared in early-stage feasibility reviews as far back as the 1980s, was studied more seriously through the 2000s, and has been included in various editions of long-term national rail planning frameworks. It is not a proposal born from impulsiveness. It is a project that China has been preparing to build intellectually, technically, politically, for roughly 4 decades. The question was never really whether to build it. The question was whether the engineering existed to build it safely. The Bo Hai Strait is not a friendly body of water. It is shallow in places, averaging around 18 meters in depth, but the geology beneath the seabed is complicated. The strait sits in a seismically active zone. The yellow sea plate and surrounding fault systems mean the rock through which the tunnel would pass is fractured, pressurized, and unpredictable. Groundwater infiltration at depth is a serious risk, and the distance involved is simply longer than any undersea tunnel built anywhere on Earth. To understand what that means in practice, consider what exists today. The Channel Tunnel between England and France stretches about 50 kilometers. The Seikan Tunnel in Japan, the previous record holder for undersea rail, runs approximately 54 kilometers. The proposed Bo Hai Tunnel would run more than 100 kilometers under the sea, nearly twice the length of either of those projects. Not twice as hard, many times harder. At that length, the ventilation requirements alone become a separate engineering challenge. Emergency evacuation protocols must be redesigned from scratch. The number of service tunnels, cross passages, and safe refuge chambers required by international rail safety standards would themselves form a small infrastructure network. The project is not just a tunnel, it is a tunnel that contains other tunnels. The tunneling approach under consideration involves twin main bores, one for each direction of travel, alongside a central service tunnel running between them. This 3-tube configuration mirrors the Channel Tunnel's layout, but at more than double the length and through far more geologically variable material. Tunnel boring machines for a project of this scale would each measure roughly 14 to 16 meters in diameter. They would need to operate continuously for years under pressures that increase the deeper and longer they travel. The machines themselves would require mid-route maintenance interventions, meaning engineers and technicians would need to enter, service, and in some cases replace components while the boring head is still deep within the seabed. That is not unusual for long tunnels. What is unusual is the scale at which every one of these standard problems must be solved simultaneously. China has been building toward this moment for a long time. The country's experience with complex tunneling has grown significantly over the past 2 decades. The construction of the high-speed rail network, the largest in the world by track length, has required tunneling through mountains, under rivers, and through urban environments at a pace and volume that no other country has matched. Chinese engineers have bored more tunnel kilometers in the past 20 years than perhaps any other nation in history. But open ocean tunneling at this length is different from mountain tunneling. The risks compound differently, and the consequences of a mistake are harder to contain. One of the central engineering concerns is what happens when water enters the bore. In mountain tunnels, groundwater infiltration is managed with drainage systems and grout injection. Under the seafloor, the hydrostatic pressure driving water toward any breach is constant and enormous. A structural failure at depth does not produce a slow leak. It can produce a catastrophic inrush. The engineering response to this problem involves a combination of ground freezing ahead of the boring head, high-pressure grout injection to pre-treat fractured zones, and tunnel lining systems designed to withstand sustained pressure from all directions simultaneously. Ground freezing, using liquid nitrogen or ammonia-based systems to turn unstable wet sediment into solid material temporarily, has been used in urban tunneling for decades. Using it in a subsea environment at this scale would be a significant technical escalation. Here, around the midpoint of construction, is where the project will face its hardest test. The central section of the Bo Hai crossing passes through a zone where the seabed geology transitions from relatively stable rock into softer, more water-saturated sediment. The boring machines will need to adapt their cutting and pressure parameters in real time as the material around them changes. A miscalibration, too much face pressure and the seabed above could destabilize, too little, and water infiltration accelerates, could force a months-long halt. This is not speculation. It is what happened during construction of the Guangzhou Metro's Pearl River crossing in the 2000s, and during several sections of Shanghai's subsea metro tunneling, though at far shorter lengths and shallower depths. The engineers on the Bo Hai project have studied those incidents carefully. In April of 2023, a team from China Railway Tunnel Group conducted additional seismic and geotechnical surveys along the proposed alignment. The results were reported to have confirmed the viability of the route while also flagging specific zones requiring enhanced ground treatment. That kind of survey, conducted decades into the planning process, is a signal of how seriously the geological uncertainty is being taken. Beyond geology, there is the question of what the tunnel is for, and whether the demand will be there when it opens. The economic logic rests on connecting Shandong and Liaoning more tightly into a single economic zone. Shandong has a GDP comparable to a mid-sized European country. Dalian is one of northeastern China's primary ports and a center of heavy manufacturing. A 40-minute rail link would, in theory, allow workers, goods and businesses to operate across both regions as if they occupied the same city. But northeastern China has faced economic headwinds for years. The old industrial base has contracted, population growth has slowed. Several major cities in Lian province have experienced population decline. Critics of the project have quietly asked whether a tunnel built for a future of expanding northeast Chinese demand is being planned for a region whose demographics are moving in a different direction. The Chinese government's answer, embedded in its regional development strategy, is that the tunnel itself will reshape the economic geography, that connectivity at this scale does not simply serve demand, but creates it. Whether that theory proves correct is a question the next generation will answer. The tunnel's completion, if current planning timelines hold, is projected sometime in the mid to late 2030s. That assumes construction begins in earnest within the next few years, which as of the most recent public statements has not yet been confirmed. The project remains in an advanced planning and feasibility stage, approved, studied, funded in principle, not yet built. That distinction matters. China has completed extraordinary projects that once seemed impossible: the Hong Kong-Zhuhai-Macau Bridge, the Qinghai-Tibet Railway, the Three Gorges Dam. It has also paused or restructured major projects when economic conditions shifted or engineering risks proved harder to manage than anticipated. The Bo Hai Strait tunnel carries a weight beyond its own construction. If it works, it will set a new standard for what undersea rail infrastructure can be. Every country planning a subsea crossing, whether across the Baltic, beneath the Red Sea, or under the Strait of Gibraltar, will study what China did here and how. If it encounters serious difficulties, those difficulties will be studied just as carefully. The strait itself has no opinion on any of this. The water moves the same way it always has, tides pushing through the narrow channel between two peninsulas, indifferent to the plans being drawn in offices hundreds of kilometers away. Somewhere beneath that water, the future of intercontinental tunneling is waiting to be proven or disproven. The story of this project is still being written,